As he said, I'm Craig. Thank you for coming. I'm here to talk about Cedar, a new authorization language that we developed at AWS. This is joint work with a whole bunch of awesome people that you see on this slide. But to start it off, what is authorization? Well, authorization is the problem of determining who can do what in a multi-user application. Authorization is a critical component of pretty much any modern web application that you'd want to build nowadays. And for example, it's about who is allowed to comment on a doc or who's allowed to view a payroll stub. Why is this a hard problem? Well, certainly the theory is known. You can go to the literature and you could read all about role-based or attribute-based or relation-based access control. The theory's been pretty well developed, in fact. But that doesn't mean that it's easy to implement permissions in your application. As an example, let's take Tiny To Do, a toy example application that allows users and teams to create, manage, and share task lists. So we have users that can be organized into teams, which can be nested, and we have task lists, which have metadata like a name and an owner, as well as actual data, a list of tasks. Tiny To Do is a web application, and its server-side or back-end code is written in Python. So here's the handler for the get list operation. It does about what you'd expect. We query the database and we return appropriate data. For the purposes of this talk, the most interesting part is the access check, because not everyone in the universe should be allowed to get data about all possible lists. So how should we implement this access check? Well, the most natural way and how it would normally be done in web applications today is by writing the logic right here in the request handler in Python. And this works, but it has a few problems. First of all, it's hard to write. We had to take all of the conditions under which access should be allowed and invert them to get the conditions under which we need to return this access denied error. We also had to get the nesting right, which is not always trivial in all cases. In fact, errors in authorization logic like this formed 4 of the top 25 common security weaknesses, or CWEs, last year. Another reason that this way of doing things is suboptimal is that it's hard to audit. If you need to go and make sure your application has done permissions correctly, or if you need to ask questions like who has access to what, you have to comb through the entire back-end code of your application. Likewise, it's hard to maintain permissions that are written this way. If you need to make a change to your application's permissions posture, you probably need to make the same change across many different request handlers, each of which will have similar but not identical code, because it's likely that slightly different rules apply to different operations. What should we do instead? Well, we should delegate the authorization decision to a dedicated authorization engine, which evaluates authorization policies written in an authorization language. This fixes a lot of the shortcomings of the previous approach. First of all, it's easier to write permissions this way. We're writing in a dedicated DSL that understands authorization concepts like permit and forbid, or like resource and principal. It's also easier to audit and maintain permissions that are written this way, because they're all stored in a single central location. If you need to check that your permissions are correct or make any changes, you only have to do that in one place, and you don't have to touch the rest of the back-end code of your application. So that's why we developed Cedar, a new authorization language focused on centralized decision-making. Cedar is at the core of 2 different AWS services, verified permissions and verified access, which have customers in many different industries, including healthcare, telecom, and asset management. But Cedar is also open source on GitHub. And as a result, it's been picked up by a number of startups, including StrongDM and Common Fate, who have built their entire core products around the Cedar authorization language. But what is unique about Cedar? Why a new authorization language? After all, there's already plenty of authorization languages that exist. Well, we identified 5 desirable properties of an authorization language, and we claim that Cedar provides a new way to balance these criteria, a new point in the design space that we think makes a lot of sense, and in particular has a focus on analyzability, which was not a focus of many previous authorization languages. Another thing that's unique about Cedar is that it is the first authorization language built from the ground up with high assurance in mind. We used an approach that we call verification guided development, and which we wrote a paper on that was actually already presented at FSE 2024 last summer. It talks about how we use formal verification and differential testing to ensure that our implementation of Cedar is correct and obeys important security properties. If you are interested in hearing about that part of the work, I highly recommend you go check out the FSE paper. But in the rest of this talk, I'm going to focus instead on what is Cedar and how do we use Cedar. So like I said, 5 desirable characteristics of an authorization language. We have ergonomics. Policies should be easy to read and write, even by non-experts. We have expressiveness. It should be possible to write authorization policies in all 3 of the major paradigms that we see in the literature: role-based, attribute-based, and relation-based access control. We have safety. We want to be able to catch policy authoring mistakes and prevent them before they cause any harm. We have performance. We want to evaluate requests quickly. And finally, we have analyzability. We want to be able to build sound policy analysis tools that enable us to reason about the permissions posture of our application and whether it respects importance, security, and variance. But the reason that these properties are challenging is that they are often in tension with each other. And in particular, the 4 properties on the right are often in tension with the one on the left, which is expressiveness. So when we were designing Cedar, we generally favored the 4 properties on the right at the expense of expressiveness. We just wanted to make sure Cedar was expressive enough to express policies in the 3 major paradigms: RBAC, ABAC, and REBAC. In particular, we drew a line in the sand around analyzability. We wanted to ensure we had a sound and complete encoding of Cedar policy semantics into decidable SMT formulas. And the word decidable is very important there. It's not just that we have a sound and complete encoding of Cedar policy semantics into SMT formulas generically, but into the decidable fragment of SMT, which ensures that we get strong and consistent performance even from our solver queries. So let's talk about each of these 5 properties, starting with expressiveness and ergonomics. Here's a Cedar policy. You already saw it a few slides ago. This policy says that anyone is allowed to take the get list action on any resource if they are in that resource's readers or editors group. The policy has 3 parts. First, we have the effect, which is either permit or forbid. Then we have the scope, which has optional constraints on the group membership or identity for the principal action and resource. So this policy has a constraint on action. So it only applies to requests where the action is exactly get list. But it does not have constraints on principal or resource, which means that so far, the policy applies to all principals and all resources. And then finally, we have conditions, which are Boolean expressions written in the Cedar language and prefixed by either when or unless, and they further constrain when the policy applies. Cedar policies are evaluated over an entity hierarchy. So in Cedar, principals, actions, and resources are all entities, and entities can be members of other entities, including recursively. So here we have a bunch of user entities that are members of team entities, which are themselves members of other team entities. And entities also have attributes, which have a name and then a type, a value of any type in the Cedar type system. So in our case, list entities have attributes like name of type string and owner of type user. So that's actually a reference to another entity in the hierarchy. Cedar requests are conceptually 3 tuples, principal, action, resource. So this request asks whether Kesha, the principal, can take the action get list on the resource list 1, 2, 3. And the request will be allowed if it satisfies at least 1 permit and no forbid policies. So this request will be allowed because resource is list 1, 2, 3. So resource.readers is the temp team, and Kesha is indeed in the temp team. But if we asked whether Emma is allowed to take the same action, that would be denied. And this is an example of an important security property of Cedar, which is that if a request matches no permit and no forbid policies, if it matches no policies at all, then it will be denied. Similar to how Neha was describing this morning for a different permission system. On the other hand, if we add back in the 2 other policies that we saw several slides ago and reissue the request with Emma, now it will be allowed because of the second policy that says anyone in the admin team is allowed to take any action on any resource. We could also ask whether Andrew is allowed to take the create list action. And you might think that that would be allowed because Andrew is also in the admin team and anyone in the admin team is allowed to take any action on any resource. However, this request would actually be denied because of the 3rd policy, which forbids anyone in the temp team from taking the create list action. And this illustrates another important security property of Cedar, which is that forbid always overrides permit. We have formal semantics for Cedar policies and how they are evaluated in the paper. So if you're interested, you can go see the paper for that. But let's move on and talk about another two properties of authorization languages, which is safety and analyzability. Cedar has a policy validator, which is essentially performs type checking. So you can declare, you can have a schema in the Cedar schema format, which declares important type level information about your application and the entities in it. And then you can validate your policies against this schema in order to catch mistakes and prevent runtime errors. So let's validate this policy. We see that the policy refers to an action called getList. So we look that up in the schema, and sure enough, there's a declaration for an action called getList, so that's valid. And furthermore, the schema tells us what principal and resource types are allowed to be used with that action. So here we see that the principal type must be user, and the resource type must be list for this action. That allows us to type check occurrences of principal and resource elsewhere in the policy. So when we see resource.readers or resource.editors, we know that resource must be of type list, and then we can see from the schema that entities of type list do have attributes called readers and editors, so that's valid. And it also tells us the type of those attributes, which allows us to type check uses of those attributes. So when we see principal in, first of all, we know that principal must be of type user from the action declaration. And then the schema also tells us that entities of type user are allowed to be in entities of type team, which makes this a valid use of the Cedar in operator, because one of the valid type signatures for the Cedar in operator says that if users are allowed to be in teams, you're also allowed to use in with user in set of team. In general, our policy validation algorithm detects improper entity relationships, unrecognized attributes, actions, and entity types, illegal operations at the type level, pretty much what you would expect from a type checking algorithm. It's a pretty standard type checking algorithm. It does have some features that you might find interesting, like flow-sensitive capability tracking. So it turns out that in Cedar schemas, you're actually allowed to declare that some attributes are optional and may or may not be present at runtime. And then Cedar policy validation actually ensures that you will never get runtime errors resulting from trying to access an attribute, an optional attribute, that did not exist at runtime. This works because validation will actually ensure that your policy must check for the existence of the attribute before it is allowed to access the attribute's value. This works via flow-sensitive capability tracking, a feature of our type system that was partially inspired by TypeScript. We then proved a soundness theorem that says that if validation succeeds, policy evaluation will exhibit no runtime type errors, or indeed a few other kinds of errors like attribute does not exist. Formal statements of this, including of our theorems and the proofs of them, are all in the paper. But in addition to validation, we also have policy analysis to reason about the semantic content of policies and answer universal questions about the behavior of policies on all possible inputs. This works via our sound and complete encoding into decidable SMT formulas. So one universal question we might be interested in is equivalence. Do two policies or two sets of policies produce the same decision on all possible inputs? This might come up in a refactoring setting. So suppose I wrote the two policies on the left. The first one says that anyone is allowed to take the create list or get own list actions. And the second one says that anyone on the intern team is actually not allowed to take the create list action. So suppose that for whatever reason, I wanted to refactor this into a single policy that had the same effect. I could do the refactoring and then invoke policy analysis, which will lower both of these policy sets into SMT formulas. And then I can ask the SMT solver, do they produce the same decision on all inputs? And of course, the SMT solver will tell me, no, they're not equivalent. And it will give me a counterexample for, in this case, that if Aaron is an intern and tries to take the get own list action, that'll produce an allow on the left and a deny on the right. So I can fix the problem and then run it back through the SMT solver, and it will tell me that they're equivalent. Formalisms for exactly how this compilation to SMT works and how we use solvers is all in the paper as well. Finally, let's talk about performance. So Cedar is written in Rust, which is one reason why it is very fast. It evaluates typical inputs in under 10 microseconds. That's microseconds, not milliseconds. And Cedar's runtime is also strictly polynomially bounded, which is in stark contrast to a lot of other authorization languages which are Turing complete and therefore have no strict bounds on their authorization time. We compared Cedar against two different open source authorization engines, Rego as well as OpenFGA, which is based on the Google Zanzibar system. And we compared all three of these engines on three different applications. Tiny To Do, which you've been seeing in this talk, as well as two applications that we borrowed from the OpenFGA examples library, one that encodes the GitHub permissions model and one that encodes the Google Drive permissions model. And we rewrote all 3 of these applications' permission systems into Cedar, Rego, and OpenFGA for this comparison. So here are the performance results. On these graphs, Cedar is in green, OpenFGA is in orange, and Rego is in blue. So you can see that as inputs get bigger along the x-axis, Cedar's performance stays strong and consistent. It's just hugging the x-axis there. You also see both solid lines and dashed lines on these graphs. The solid lines represent median performance, and the dashed lines represent the 99th percentile performance, or P99. You can see that even Cedar's P99 is strong and consistent. In conclusion, Cedar provides expressive, fast, safe, and analyzable authorization. It is open source on GitHub. Come check us out. And we also have a website where you can find a playground, tutorials on how to use Cedar. Last but not least, we are hiring applied scientists to work on Cedar. So if that's you, or you think it might be you, or you're just interested in talking about what that might look like, come find me after or email me at this address. Thanks, and I'm happy to take questions.
Questions? Then there's a mic in the middle.
Thank you for the presentation. I was actually today at the keynote at 9 a.m. where Neha was talking about using Daphne to do, I think, similar things. Does Cedar have like any interop capabilities with Daphne, or is it like a completely separate? Are they like responsible for completely separate things?
So Cedar, there are a couple answers. First of all, Cedar is a completely different system than the IAM system that Neha was talking about at the keynote. The IAM system that she was talking about is used by AWS to control access to its own principles and resources. And Cedar is sort of a reimagined version of it with lessons learned, and also that allows you to control access to your own application's resources. So it's much more generic in that sense. But the other answer that I'll give to your question is that we do have a formalization of Cedar in Lean, and that we prove theorems about it. And that's discussed a lot more in the FSE paper that I referenced early on in the talk.
Awesome. Do you plan on replacing the entire like Daphne workflow with Cedar in the future, or?
We have no plans to do that.
Okay, thank you.
Hi, really cool talk. At lunch, I heard Armando talk about program synthesis, and now I come here and there's a set solver, there's these properties that we want. So have you thought about probably leveraging the set solver not only to prove that certain properties always hold or never hold or something like that, but also actually to help people write these things? So maybe I have a permission that I'm not sure how to write, I'll leave a hole and maybe the set solver can help me. Have you given that any thought?
Yeah, I haven't given that very much thought, but it does sound like a great idea. I think that one of the problems you're going to run into is coming up with a good enough spec for what the policy should do that is constraining the sat solver enough to like come up with the right answer, right? We've found that people have a hard time writing specifications about their authorization system. It's not a way that people are generally used to thinking. In this community, we do it a lot, but like engineers in the world, it's sometimes hard to express the invariance that you're thinking about.
Okay, well, thank you.
As we go to the last question, maybe Ethan, you can set up.
Really cool talk. I had a kind of a vague question, which is like you described this as being a new, particularly well-informed point in the design space, which makes sense. Do you see like the future of programming language design as being just continuing to learn lessons and carve out better and better sets of points in the design space of possible DSLs? Or is there like a future in which there's maybe a continuum? Like, I don't know. It's kind of a vague question, but I'm curious to hear your thoughts.
I mean, so I think that definitely we are going to continue to learn lessons and try to design DSLs that strike better and better balances. But I also think that that's a pretty small vision for what the entire future of programming languages will be. I think that we also are going to continue to see big ideas and programming languages that look nothing like the languages we've seen before. You know, this community has come up with a lot of really radical ideas for what languages should look like, and I hope we see more of that in the future too.
Cool. Thanks.
All right, perfect timing. Let's thank Craig one more time.